Welcome to Still Science Lab. Tonight, we embark on a journey into the very fabric of existence to explore the space-time fabric, the invisible architecture of reality. For most of human history, we have perceived the world as a stage, a fixed, three-dimensional box where events happen in a separate, linear flow called time. But as we will discover tonight, this intuition is the greatest illusion ever cast upon the human mind. The reality of our universe is far more strange and interconnected than our senses could ever suggest. We are not moving through space and through time as two distinct entities. Instead, we are woven into a single, four-dimensional continuum known as space-time. To understand this is to pull back the curtain on the most fundamental secret of the cosmos, revealing that everything we see, feel, and experience is governed by a structure that is both invisible and omnipresent. For centuries, our understanding of the universe was anchored by the towering genius of Isaac Newton. To Newton, space was an absolute, unchanging void, an infinite container that existed regardless of whether anything was in it. Time, similarly, was seen as an absolute arrow that marched forward at the same steady rate for everyone, everywhere, regardless of their motion or location. This Newtonian worldview was incredibly successful. It explained the motion of the planets, the fall of an apple, and the tides of the oceans. It gave us a universe that felt like a predictable, clockwork machine. In this world, if you and I both looked at our watches, we would agree on the duration of a second, and if we measured a meter stick, we would agree on its length, no matter how fast we were moving relative to each other. This was the common sense of physics, and it remained unchallenged for over 200 years because, at the slow speeds of human life, it works perfectly. However, toward the end of the 19th century, a crack began to appear in this clockwork universe. The problem came from an unexpected source: the study of light. James Clerk Maxwell had successfully unified electricity and magnetism into a single set of equations, which predicted that light was an electromagnetic wave traveling at a constant speed, denoted as c, which is approximately 299,792,458 meters per second. But Maxwell's equations presented a radical problem. They didn't say what light was moving relative to. In the Newtonian world, speeds are always additive. If you are on a train moving at 50 kilometers per hour and you throw a ball forward at 10 kilometers per hour, an observer on the ground sees the ball moving at 60 kilometers per hour. Logic suggested that if Earth was moving through space, we should measure different speeds of light depending on which direction we were looking. This led to the famous Michelson-Morley experiment in 1887, one of the most important failures in the history of science. They attempted to detect the ether, the supposed medium through which light traveled, much like sound travels through air. If the ether existed, the Earth's motion through it should create an ether wind, causing light to travel at different speeds in different directions. To their shock, the result was a null. No matter which way the Earth moved, the speed of light remained exactly the same. The Newtonian addition of velocities had failed. This was the crisis that set the stage for a young Albert Einstein to rethink the very nature of reality. Einstein realized that if the speed of light is indeed a universal constant, a fundamental law of nature that remains the same for all observers, then our basic assumptions about space and time must be wrong. Einstein's radical insight was that space and time are not independent, absolute quantities. Instead, they are relative and deeply intertwined. To keep the speed of light constant for everyone, space must contract and time must dilate, depending on an observer's motion. This was the birth of special relativity. But the true architectural breakthrough came shortly after, in 1908, when Einstein's former teacher, Hermann Minkowski, realized the mathematical implications of these ideas. Minkowski famously declared that from henceforth, space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. This union is what we now call space-time. Imagine a map. To find a location, you need 3 coordinates: latitude, longitude, and altitude. This defines a point in 3-dimensional space. But in our universe, a point is not enough to describe an event. To meet a friend, you don't just need to know the location, the coffee shop on the 3rd floor. You also need to know the 4th coordinate, time, at 3 p.m. In the Newtonian view, that 4th coordinate was just a label. In the Minkowski view, time is a dimension just like the others, but with a unique mathematical property. We live in a 4-dimensional world where every point is an event in space-time. The distance between 2 events is not just a spatial distance or a time interval, but a space-time interval. This fusion creates a profound shift in how we view the now. On Earth, we feel like there is a universal now happening across the entire universe simultaneously. But because of the way space-time is structured, absolute simultaneity does not exist. 2 events that appear to happen at the same time for you might happen at different times for someone moving at a different velocity. This is not an optical illusion or a delay in signal. It is a fundamental property of the geometry of the universe. Time is not a universal river. It is a personal experience that depends on your path through the 4-dimensional fabric. The faster you move through the 3 dimensions of space, the slower you move through the dimension of time. It is as if you have a fixed budget of motion through space-time, and you must choose how to distribute it. The concept of the space-time fabric allows us to visualize the universe as a block. In this block universe model, the past, the present, and the future all exist simultaneously as a 4-dimensional structure. Just as New York, London, and Tokyo all exist at once on a map, even if you are currently only in one of them, every moment of your life exists as a coordinate in the fabric of space-time. The flow of time that we perceive, the feeling of the present moving forward, is a result of our biological consciousness processing these coordinates. This suggests that the distinction between past and future is, as Einstein once wrote in a letter of condolence, only a stubbornly persistent illusion. Understanding space-time as a single, unified fabric is the essential first step to unlocking the rest of physics. It is the canvas upon which gravity, light, and matter are painted. Without this unification, we could never explain why GPS satellites, moving at high speeds above the Earth, must constantly correct their clocks to account for the stretching of time. We could never explain why cosmic rays can reach the Earth's surface before decaying. The great illusion of separate space and time was shattered by the realization that we are part of a dynamic, elastic geometry. As we peel back the layers of this invisible architecture, we must confront the guardrail that keeps this whole structure from falling into chaos. If space and time can stretch and shrink, what remains solid? What prevents the universe from being a soup of unpredictable events? The answer lies in the one thing that never changes, the cosmic anchor that defines the scale of reality itself. In our next chapter, we will look closely at the cosmic speed limit and discover why the speed of light is not just a speed, but the very stitching that holds the four dimensions of space-time together. To understand why the universe is shaped the way it is, we must confront a value that is often misunderstood as merely a very fast speed. In our daily lives, we are accustomed to the idea that speeds are relative and additive. If you walk down the aisle of a moving train, your speed relative to the tracks is the sum of your walking pace and the train's velocity. We assume that with enough power, any speed is reachable. But the universe has a hard, unbreakable ceiling. This is the value denoted as c, approximately 299,792,458 meters per second, commonly known as the speed of light. However, calling it the speed of light is almost a disservice to its true importance. Light travels at this speed not because of any special property of photons, but because c is the fundamental speed of information and causality. It is the maximum rate at which any effect in the universe can follow a cause. It is the stitching that holds the four dimensions of space-time together, acting as the conversion factor between space and time. In this second chapter, we explore why this cosmic speed limit is the bedrock of reality and what happens when we try to challenge the unbreakable laws of the fabric. The realization that c is a constant, regardless of the observer's motion, was the spark that ignited the revolution of modern physics. If you were in a spaceship traveling at 99% the speed of light and you turned on a flashlight, Newtonian logic suggests that the light should move away from you at the speed of light relative to your ship, meaning it would be traveling at nearly 200% of c relative to a stationary observer. But nature refuses this math. Every experiment ever conducted confirms that both you and the stationary observer would measure the light from that flashlight at exactly c. This consistency is the central pillar of the universe. Because the speed of light cannot change, something else must. For the speed, distance divided by time, to remain constant for everyone, the very measures of distance and time must warp. If two observers in different states of motion are to agree on the speed of light, they must disagree on the length of a meter and the duration of a second. This is the profound truth of the cosmic speed limit. It is the only fixed thing in a universe where everything else is fluid. To visualize why c is the conversion factor between space and time, consider how we use units of measurement. On a standard map, we might see a scale where 1 centimeter represents 1 kilometer. This scale allows us to convert a measurement on the paper into a measurement in the physical world. Space-time functions in a similar way. Because we perceive space and time as different things, we measure them with different units, meters, and seconds. However, c tells us that they are actually parts of the same fabric. In the geometry of space-time, 1 second is exactly equal to 299,792,458 meters. When you move through the universe, you are always traveling at exactly c through the four-dimensional block of space-time. If you are sitting perfectly still in space, you are moving through the dimension of time at the maximum rate. As you begin to move through space, you must borrow some of that motion from your time dimension. The faster you go through space, the slower you must go through time to ensure that your total velocity through space-time always equals c. This is why c is not just a speed limit for light. It is the universal constant of motion for every object in existence. The reason we cannot reach or exceed this speed limit lies in the relationship between energy and mass, famously captured in the equation E equals mc2. On Earth, we think of mass as a constant. An object weighs what it weighs. But mass is actually a measure of an object's energy content and its resistance to acceleration or inertia. As an object with mass is pushed closer and closer to c, the energy you pump into it to make it go faster doesn't just increase its velocity, it also increases its relativistic mass. The closer you get to the speed of light, the heavier and more resistant to further acceleration the object becomes. To reach c, an object with even the smallest amount of mass would become infinitely heavy and require an infinite amount of energy to push it that last fraction of a percent. This is why only massless particles, like photons, can travel at the cosmic speed limit. They are born traveling at c and can never travel at any other speed. For anything made of atoms, c is a literal wall that the laws of physics will not allow us to scale. But why does this limit exist at all? Why couldn't the universe function with infinite speed? The answer is found in the concept of causality. Causality is the principle that a cause must always precede its effect. If you throw a stone into a pond, the ripples must appear after the stone hits the water. In a universe with no speed limit, or where information could travel faster than c, this fundamental sequence of logic would collapse. Because of the way space-time is linked, traveling faster than c is mathematically equivalent to traveling backward in time. If information could move at an infinite speed, an observer in a different frame of reference could see an effect happen before its cause. You could, in theory, receive a message answering a question you haven't asked yet, or see a glass shatter before it was dropped. The cosmic speed limit is the universe's way of protecting the sequence of events, ensuring that the past remains the past and the future remains the future. It is the logical speed of reality. This limit also defines the boundaries of what we can ever know or influence. Scientists use the concept of a light cone to describe this. Imagine an event happening right now, say, a star exploding. That event creates a future light cone that expands at the speed of light. Anything outside that cone is physically incapable of being affected by that explosion because no signal can reach them fast enough. Similarly, we are at the tip of our own past light cone. We can only see stars whose light has had enough time to reach us. When we look at the night sky, we are not seeing the universe as it is now. We are seeing a history book. We see the moon as it was 1.3 seconds ago, the sun as it was 8 minutes ago, and distant galaxies as they were billions of years ago. The cosmic speed limit turns the universe into a giant time machine, where the further we look into space, the further we are looking back into the history of space-time. The limit of c also explains why the universe appears so vast and empty. Even at the fastest possible speed, it takes years to reach the nearest stars and billions of years to cross the gaps between galaxies. This creates a kind of cosmic isolation. Each part of the universe is effectively sequestered from the others by the sheer time it takes for information to travel. This suggests that the speed of light is not just a physical constant, but a structural boundary that determines the scale of everything we can interact with. If c were much faster, the universe would feel much smaller. If it were slower, every star system would be a lonely island, entirely cut off from the rest of existence. As we move forward in our investigation of the space-time fabric, we must recognize that the constancy of c is what causes the bending of our perception. Because c is rigid, time and space must be elastic. This elasticity is not just a theoretical curiosity. It is a physical reality that has profound consequences for anyone traveling at high speeds. To truly understand the architecture of reality, we must look at what happens to a clock when it moves, and why the present moment is a myth that varies from person to person. In our next chapter, we will step onto a metaphorical cosmic train and explore the elasticity of time, discovering why your age is not a fixed number, but a variable determined by your journey through the fabric. The realization that the speed of light is a universal constant forces us to abandon our most cherished intuition, the idea that time flows at the same rate for everyone, everywhere. If you and I are to agree on the speed of light while moving at different velocities, our personal clocks must tick at different speeds. This is the phenomenon of time dilation, a direct consequence of the elasticity of the space-time fabric. In our daily lives on Earth, we move so slowly compared to the cosmic speed limit that time feels rigid and absolute. A second seems to be a second whether we are sitting in a chair or flying in a jet. But as we move closer to the speed of light, the temporal dimension begins to stretch in ways that challenge our very understanding of what it means to exist in the present moment. Time is not a universal river that carries us all at the same pace. It is a personal experience, a coordinate in space-time that is as flexible as the distance between 2 points on a rubber sheet. To visualize why time must slow down as you move faster, we look at one of Einstein's most famous thought experiments involving what is called a light clock. Imagine a clock consisting of two mirrors, one placed directly above the other, with a single particle of light, a photon, bouncing back and forth between them. Each time the photon hits a mirror, the clock ticks. If this clock is sitting still on a table in front of you, the photon travels a simple, straight vertical path up and down. But now, imagine that same clock is inside a transparent spaceship flying past you at half the speed of light. From your perspective outside the ship, the photon is no longer moving just up and down. Because the ship is moving forward at an immense speed, the photon must travel a diagonal, zigzag path to reach the next mirror. This diagonal path is significantly longer than the straight vertical path the photon takes when the clock is at rest. Here is where the unbreakable nature of the speed of light changes everything. Since light cannot speed up to catch up with the moving mirrors, and since it must travel a longer distance to complete one tick from your perspective, it must take more time to finish that journey. Therefore, as you watch the clock on the moving ship, you see it ticking slower than your own. This is not a mechanical failure of the clock, nor is it an optical illusion. It is a fundamental stretching of time itself. Every biological and physical process inside that ship, the beating of a heart, the chemical reactions in a brain, the aging of cells, and the decay of atoms, slows down in exact proportion to the clock. If you could see the face of the astronaut inside, they would appear to be moving in slow motion. Yet, for the astronaut inside the ship, everything feels perfectly normal because their own perception of time is tied to that same slowed down fabric. This relationship is defined by a mathematical factor that grows as velocity increases. As an object's speed approaches the limit of light, the stretching of time becomes extreme. This leads us to the famous scenario known as the twin paradox. Imagine two identical twins. One twin stays on Earth while the other boards a high-speed spacecraft and travels to a distant star system at 99% the speed of light. When the traveling twin returns home, they find a shocking reality. While they may have only aged a few years during their journey, their sibling on Earth has aged by decades. The traveler has literally moved into the Earth's future. This is not science fiction. It is a documented reality of how our universe functions. The traveling twin has moved through less of the time dimension because they moved through more of the spatial dimensions. By moving through space so rapidly, they traded their motion through time for motion through the physical void. The elasticity of time also shatters the concept of absolute simultaneity. The idea that there is a single now happening across the entire universe. On Earth, we believe that while we are speaking, something is happening at the same time on Mars or in a distant galaxy. However, because space and time are linked, different observers will disagree on the order of events depending on how they are moving. If two lightning bolts strike the ground at different locations, one person standing still might see them happen at exactly the same time, but another person flying past at high speed might see the bolt in front of them strike before the bolt behind them. Because the speed of light is the same for both, and their paths through space-time are different, both observers are technically correct. There is no universal clock in the sky that keeps the master time for the cosmos. Your now is not the same as someone else's now if you are moving relative to one another. We see the proof of this temporal elasticity every day in the subatomic world. High in our atmosphere, cosmic rays collide with air molecules, creating particles called muons. These particles are highly unstable and decay in an incredibly short amount of time, about 2 millionths of a second. Even traveling at nearly the speed of light, a muon should only be able to travel a few hundred meters before it vanishes, meaning they should never reach the ground. Yet, detectors on the Earth's surface find them in great numbers. The reason is time dilation. Because the muons are moving so fast, their internal clocks are slowed down from our perspective. For the muon, only a fraction of a second passes, allowing it to reach the surface. From its own perspective, the distance it has to travel is contracted, but the result is the same. The elasticity of space-time allows the particle to survive a journey that should be impossible. Even our modern technology would fail if we did not account for this stretching of time. The Global Positioning System, or GPS, relies on a network of satellites orbiting the Earth at high speeds. These satellites carry incredibly precise atomic clocks. Because they are moving at thousands of miles per hour relative to the ground, their clocks tick slightly slower than the clocks on our phones. Furthermore, because they are further away from the Earth's mass, they experience a different gravitational effect on time, which we will explore in a later chapter. If engineers did not use Einstein's equations to constantly correct for these tiny differences in the flow of time, the GPS on your phone would lose its accuracy by several kilometers every single day. The very fact that you can navigate to a coffee shop using your smartphone is a daily confirmation that time is elastic. This reveals that the space-time fabric is not a rigid grid, but a dynamic and responsive medium. Time is a dimension that can be molded, stretched, and squeezed by motion. It tells us that the universe is not a static place where things just happen. It is a four-dimensional structure where our journey through space determines our journey through time. But motion is not the only thing that can stretch the fabric. Just as a heavy object placed on a trampoline causes the fabric to sag and stretch, mass itself has a profound effect on the geometry of existence. If velocity can slow time down, we must ask, what happens to the fabric of reality when a planet, a star, or a massive black hole is involved? The answer moves us from the specific rules of motion into the grand architecture of gravity. In our next chapter, we will look at how mass tells space-time how to curve and why you are currently being held in your seat not by a mysterious pulling force, but by the invisible slope of the ground beneath you. For nearly 300 years, the world followed Isaac Newton's vision of gravity as a mysterious, invisible tether, a force that reached out across the void of space to pull objects toward one another. Newton's equations were brilliant, allowing us to predict the motion of the planets and the fall of an apple with staggering precision. But there was a deep underlying problem that Newton himself acknowledged. He had no idea how gravity actually worked. He called it action at a distance, a concept that felt almost like magic. Furthermore, as we discovered in the previous chapters, the universe has a strict speed limit. If the sun were to suddenly vanish, Newton's theory suggested that the Earth would fly out of its orbit instantly. But Einstein realized that nothing, not even gravity, can travel faster than the speed of light. If the sun disappeared, we wouldn't know it, and we wouldn't feel the change in gravity for 8 minutes. This led to a radical reimagining of the universe. Gravity is not a force that travels through space. Gravity is the very shape of space itself. In this fourth chapter, we explore the geometry of gravity and how mass dictates the architecture of the space-time fabric. To understand Einstein's breakthrough, we must first look at his happiest thought, which scientists call the equivalence principle. Imagine you are inside a windowless elevator in the middle of deep space, far away from any stars or planets. You would feel weightless, floating in the center of the room. Now, imagine a rocket engine attaches to the bottom of the elevator and begins to accelerate it upward at 9.8 meters per second squared. Suddenly, you would feel yourself pressed against the floor. If you dropped a ball, it would fall to the floor just as it does on Earth. Einstein realized that there is absolutely no experiment you could perform inside that box to tell the difference between being accelerated through space and standing still on the surface of a planet. Gravity and acceleration are fundamentally the same thing. This was the key that unlocked the door to general relativity. If acceleration is just a change in your path through space-time, then gravity must be a property of that path as well. This led to the famous analogy of the trampoline or the rubber sheet. Imagine the space-time fabric as a vast, flat, two-dimensional sheet of rubber stretched tight. If you place a heavy bowling ball in the center of the sheet, it creates a deep well, stretching and curving the rubber around it. This bowling ball represents a massive object like the sundae. Now, if you roll a smaller marble across the sheet, it won't move in a straight line. Instead, it will follow the curve of the well, circling the bowling ball or spiraling inward. To an observer who can't see the curve in the sheet, it looks like the bowling ball is pulling the marble with an invisible force. But in reality, there is no pull. The marble is simply following the straightest possible path it can in a space that has been warped and distorted. This is the essence of gravity. Mass tells space-time how to curve, and space-time tells mass how to move. In this four-dimensional geometry, what we perceive as an orbit is actually a geodesic. A geodesic is the shortest path between 2 points in a curved space. On a flat map, the shortest path between two cities is a straight line, but on the curved surface of the Earth, the shortest path is a great circle arc. When the Earth orbits the Sun, it isn't being held by a string or pushed by a force. It is simply traveling in a straight line through a space-time that has been curved into a circle by the Sun's immense mass. You are sitting in your chair right now not because the Earth is reaching up to grab you, but because the mass of the Earth has warped the space-time around you so severely that the natural straight path for your body is toward the center of the planet. Your chair is a mechanical device that is constantly pushing you away from your natural path, and that resistance is what you feel as your weight. One of the most profound proofs of this geometric reality came from the way gravity affects light. In Newton's world, light having no mass should be unaffected by gravity. But in Einstein's world, light must follow the curvature of the fabric. If space-time is curved, even a beam of light must bend as it passes near a massive object. This was famously tested during the solar eclipse of 1919. Astronomers led by Arthur Eddington traveled to the island of Principe to observe stars near the edge of the sun during the eclipse. They found that the positions of the stars appeared to shift exactly as Einstein's equations predicted. The sun's mass was literally acting like a lens, bending the light of distant stars as it passed through the warped space around it. This phenomenon is known as gravitational lensing, and today we use it to see galaxies that are billions of light years away, hidden behind closer clusters of stars. The universe is full of these cosmic magnifying glasses, created by the deep wells in the space-time fabric. However, we must remember that this fabric is not just space, it is space-time. When a massive object curves the fabric, it doesn't just distort the three dimensions of length, width, and height, it also distorts the fourth dimension of time. This is where the geometry of gravity becomes truly mind-bending. Because space and time are inextricably linked, you cannot curve one without stretching the other. In the vicinity of a massive object, where the curvature is greatest, the very ticks of the cosmic clock are slowed down. This is called gravitational time dilation. If you were to stand on the surface of a massive star, time would pass more slowly for you than for someone floating in the empty void of space. The deeper you are in a gravitational well, the slower your personal clock ticks relative to the rest of the universe. This means that gravity is not just a shaper of planets and galaxies, it is a ruler of time itself. Every mountain, every planet, and every black hole is a temporal anchor, slowing down the flow of reality in its immediate neighborhood. This geometric distortion is what creates the flow we experience. We are not just moving through space, we are falling through a four-dimensional landscape where the hills and valleys are made of time and space intertwined. As we look deeper into this architecture, we see that the curvature can become so extreme that it threatens to tear the fabric altogether. But before we reach those breaking points, we must understand the practical consequences of this temporal stretching. In our next chapter, we will move from the shape of the fabric to the theft of time, exploring why a clock at the top of a skyscraper ticks faster than one at the bottom, and why the most massive objects in the universe are the ultimate thieves of time. In our previous investigation, we looked at the trampoline of existence and saw how mass dictates the geometry of space. But we must remember that the fabric we are discussing is not just a three-dimensional stage. It is a four-dimensional continuum. If mass curves the spatial dimensions of length, width, and height, it must, by the very definition of the union of these dimensions, curve the temporal dimension as well. This brings us to a phenomenon that is as unsettling as it is profound: gravitational time dilation. It is the realization that gravity is not just a shaper of orbits and planets, but a literal thief of seconds. The deeper you reside in a gravitational well, the closer you are to a massive object like a planet or a star, the more slowly your personal clock ticks relative to the rest of the universe. Time is not a steady, universal heartbeat. It is a fluid that slows down in the presence of mass. In this fifth chapter, we explore how gravity stretches the moments of our lives and why the ground beneath your feet is constantly tugging at the very flow of your reality. To grasp why gravity has the power to slow down time, we return to Einstein's equivalence principle. We establish that being in a state of gravitational pull is indistinguishable from being in a state of acceleration. Imagine once more that you are in a rocket ship, accelerating upward through deep space. Suppose you have two clocks, one at the nose of the ship and one at the tail. If you send a light signal from the tail to the nose of the ship is constantly moving away from the light signal as it travels. By the time the light reaches the observer at the front, the ship has gained more speed. This causes a phenomenon known as the Doppler shift, where the light appears to have a lower frequency it is stretched out. In the context of time, frequency is essentially the rate of a clock's ticks. Because acceleration and gravity are the same, this same stretching happens in a gravitational field. If you are standing at the base of a massive tower and send a light signal to the top, the gravity of the Earth stretches the light as it climbs out of the gravitational well. This is called gravitational redshift. To an observer at the top of the tower, the light pulses from the bottom arrive more slowly than they were sent. Therefore, from the perspective of the person at the top, the clock at the bottom is ticking in slow motion. This is not a mere theoretical curiosity. It is a physical reality that has been measured with extreme precision. In 1959, the Pound-Rebka experiment at Harvard University used a tower only 22.5 meters tall to prove this. They used highly sensitive gamma-ray detectors to measure the change in the frequency of light as it traveled from the basement to the roof. Even over such a tiny distance, the Earth's gravity was enough to measurably shift the frequency of the light. The experiment proved that time really does flow differently at different altitudes. You are, quite literally, aging more slowly at your feet than you are at your head. Of course, on a planet as small as Earth, these differences are incredibly minute fractions of a billionth of a second over a lifetime. But they are the fundamental consequences of living in a universe where mass curves the fabric of space-time. We see this time theft in action every time we use our modern technology. As we discussed in Part 3, the satellites that power our GPS systems are moving at high speeds, which causes their clocks to slow down due to special relativity. However, these satellites are also 20,000 kilometers above the Earth's surface. Because they are further away from the Earth's mass, they are in a shallower part of the gravitational well. In this region, time flows faster than it does on the ground. The gravitational effect actually speeds up their clocks by about 45 microseconds per day, while their motion slows them down by about 7 microseconds. When you combine these two effects, the clocks on GPS satellites run about 38 microseconds faster every single day compared to clocks on Earth. If the engineers did not account for this gravitational time thief, the location data on your phone would drift by more than 10 kilometers in a single day. Our global navigation, our financial markets, and our communication networks are all built on the reality that time is a variable determined by gravity. As we move away from Earth and look at the more massive objects in our galaxy, the theft of time becomes grand larceny. Imagine a white dwarf, the collapsed core of a dead star, about the size of Earth but with the mass of the Sunday. The gravity on its surface is so intense that if you were to stand there, your personal clock would tick significantly slower than a clock back on Earth. But even a white dwarf is nothing compared to a neutron star. A neutron star is an object so dense that a single teaspoon of its material would weigh billions of tons. On the surface of a neutron star, gravity is so powerful that time is slowed by nearly 30%. If you could somehow survive standing on a neutron star for 7 years, when you return to Earth, 10 years would have passed. The geometry of the star has warped the space-time fabric so severely that the very now has been stretched to a breaking point. This leads us to a fascinating biological perspective on our own lives. If gravity slows time, does that mean you can live longer by staying at sea level? Technically, yes. A person living at the beach is closer to the center of the Earth's mass than a person living on the peak of Mount Everest. Over the course of a 70-year life, the person at the beach will have aged about 90 microseconds less than the mountaineer. While this is far too small for a human to perceive, it demonstrates that we are all walking through a landscape of varying time rates. We are not just moving through space, we are swimming through a temporal sea where the currents are dictated by the presence of every rock, every mountain, and every planet. Your experience of the passage of a second is a local phenomenon, unique to your specific position in the gravitational architecture of the universe. The most extreme version of this phenomenon occurs at the edge of a black hole, a place where the curvature of space-time becomes infinite. As an object approaches the event horizon of a black hole, time dilation reaches such an extreme that, to a distant observer, the object appears to slow down, freeze, and eventually fade away, never actually crossing the threshold. From the perspective of the falling object, however, time seems to pass normally, but the rest of the universe appears to speed up into a frantic blur. We will dive deeper into this existential breakdown in Part 7, but it is important to understand that the time thief is not just a quirk of physics, it is the ultimate boundary of our reality. It suggests that time is not something we possess, but something we inhabit, and its rate is a gift from the geometry of the world around us. This realization transforms our understanding of history and the future. If time is elastic and tied to gravity, then the age of the universe is also a matter of perspective. A clock in the deep voids between galaxies, far from the influence of any mass, has ticked more times than a clock near the center of a galaxy. The universe has many different ages, all happening at once in different layers of the space-time fabric. This removes the idea of a universal present and replaces it with a beautiful, complex mosaic of local times. We are all living in our own personal temporal bubbles, shaped by the mass of the Earth, the Sun, and the stars. As we continue to peel back the layers of this invisible architecture, we realize that if the fabric of space-time can be stretched and curved, it can also vibrate. Just as a stone thrown into a pond creates ripples that travel across the water, the movement of massive objects creates ripples in the very fabric of reality itself. These are not ripples of sound or light, but ripples of space and time. In our next chapter, we will explore these ripples in the void gravitational waves and how they allow us to hear the most violent and silent events in the cosmos. From the collision of black holes to the very echo of the Big Bang, for generations, our understanding of the cosmos was limited by what we could see. From the first primitive telescopes to the sophisticated orbiting observatories like Hubble and James Webb, we have been students of light. We analyzed the glow of stars, the infrared heat of distant nebulae, and the faint radio whispers of the early universe. But light, for all its brilliance, is only one way of perceiving reality. It is an electromagnetic wave that travels through space, but it does not tell us anything about the nature of space itself. In the previous chapters, we established that space-time is a physical, elastic fabric that can be stretched by motion and curved by mass. If this fabric is truly a medium, then it stands to reason that it can also vibrate. Just as a drumhead ripples when struck, or a pond waves when a stone is cast into its depths, the very geometry of the universe can be set into motion. These are the ripples in the void gravitational waves, and their discovery has provided humanity with a new sense that allows us to hear the most violent, silent, and ancient events in the history of the cosmos. In this sixth chapter, we move from the static curvature of gravity to the dynamic vibration of the fabric itself, exploring how the universe speaks through the language of pure geometry. The theoretical foundation for these ripples was laid by Albert Einstein in 1916, shortly after he completed his general theory of relativity. He realized that if mass curves space-time, then an accelerating mass must create a changing curvature that propagates outward at the speed of light. Imagine two massive stars orbiting each other in a frantic cosmic dance. As they swing around their common center of gravity, they are constantly stirring the space-time fabric around them. This stirring sends out waves of gravitational energy that stretch and squeeze the distance between points in space as they pass. However, Einstein was deeply skeptical that we would ever detect them. He calculated that the effect of these waves would be so incredibly faint that by the time they reached Earth from a distant source, the distortion they caused would be smaller than the width of a single atomic nucleus. For nearly a century, gravitational waves remained a mathematical ghost, a predicted consequence of relativity that seemed destined to stay beyond the reach of human observation. To understand why these ripples are so difficult to detect, we must look at the stiffness of space-time. Although we describe it as a fabric or a rubber sheet, space-time is actually the most rigid material in existence. It takes a truly cataclysmic amount of energy to make it vibrate in any measurable way. The ripples created by our own movements, or even the movements of the planets in our solar system, are so infinitesimal that they are effectively non-existent. To find a ripple we can actually measure, we have to look for the most extreme events in the universe: the collision of black holes or the merger of neutron stars. When two black holes, each dozens of times more massive than our Sun, spiral into each other at half the speed of light, they release more energy in a fraction of a second than all the stars in the observable universe combined. Yet, because space-time is so stiff, this titanic explosion of energy arrives at Earth as a distortion so small it defies imagination. The breakthrough came with the construction of the Laser Interferometer Gravitational Wave Observatory, or LIGO. These facilities, located in Washington and Louisiana, are among the most precise measuring instruments ever built by human hands. Each LIGO detector consists of two 4-kilometer-long arms arranged in an L shape. A laser beam is split and sent down both arms, bouncing off mirrors at the ends to return to a central point. If a gravitational wave passes through the Earth, it will literally stretch one arm of the detector while squeezing the other. This change in length shifts the way the laser beams overlap, creating a pattern that scientists can measure. But the scale of this measurement is staggering. To detect a gravitational wave, LIGO must measure a change in the length of its arms that is 1,000th the width of a proton. It is equivalent to measuring the distance to the nearest star, 4 light-years away, with an accuracy thinner than a human hair. On the 14th of September 2015, the ghost was finally caught. For the first time in history, the space-time fabric vibrated in a way that we could record. The signal, known as GW150914, was the chirp of two black holes merging 1.3 billion light-years away. As the wave passed through the LIGO detectors, it caused the 4-kilometer arms to flicker by that microscopic fraction of a proton's width. In that moment, humanity stopped being deaf to the universe. We weren't looking at light. We were feeling the actual contraction and expansion of the space we inhabit. This discovery confirmed Einstein's final great prediction and opened a new era of multi-messenger astronomy. We can now observe events that emit no light at all, such as the silent union of black holes in the dark heart of a distant galaxy. When a gravitational wave passes through your body, it does something truly remarkable. It changes your physical dimensions. As the ripple moves through you, the space between the atoms in your body is stretched in one direction and squeezed in the other. For a brief moment, you become slightly taller and thinner, then slightly shorter and wider. However, because the wave is so weak, this change is billions of times smaller than anything your nerves could ever feel. Even if a wave from a nearby supernova passed through you, you would remain completely unaware of the fact that your physical form was being distorted by the geometry of the universe. This reminds us that we are not just objects sitting on top of space-time. We are part of it. When the fabric ripples, we ripple with it. The importance of these waves extends far beyond just proving Einstein right. They are a form of cosmic archaeology. Unlike light, which can be blocked by dust, absorbed by gas, or distorted by gravity, gravitational waves travel through the universe almost entirely unimpeded. They carry a perfect, pristine record of the event that created them. This means we can use them to look back at the very beginning of the universe. Scientists believe that the Big Bang itself created a stochastic background of gravitational waves, a permanent hum of ripples from the moment the universe was born. If we can detect these ancient waves, we will be able to see further back in time than is possible with any telescope, reaching the very first fraction of a second of existence. Furthermore, gravitational waves allow us to test the laws of physics in the most extreme environments imaginable. By analyzing the shape of the waves produced by merging black holes, we can check if general relativity holds true even when gravity is at its most intense. So far, Einstein's equations have passed every test with flying colors. The ripples in the void tell us that the universe is a coherent, mathematical whole, where the same rules that govern an apple falling on Earth also govern the collision of giants across the billion light-year expanse. We are learning to listen to the music of the spheres, a symphony of vibrations that tells the story of birth, death, and transformation on a scale that humbles our earthly concerns. As we master this new way of perceiving the space-time fabric, we find ourselves drawn toward the sources of the most powerful ripples. These are the places where the fabric doesn't just vibrate, but where it is twisted and torn into the most mysterious shapes in nature. If gravitational waves are the ripples on the surface of the pond, then black holes are the whirlpools where the water disappears entirely. In our next chapter, we will travel to the event horizon, the ultimate boundary of space-time, where the laws of physics as we know them begin to dissolve and where the concept of time itself may come to an end. We will explore what happens when the architecture of reality reaches its breaking point and whether anything can survive the encounter with the infinite. In our journey through the invisible architecture of the cosmos, we have seen the space-time fabric stretch with motion, curve with mass, and ripple with the violent collisions of giants. We have learned that we live in a universe where the geometry of space and the flow of time are not fixed, but are dynamic participants in the story of reality. However, everything we have discussed so far, the bending of light, the slowing of clocks, the vibration of waves, occurs in regions where the fabric of space-time, though distorted, remains intact. But there are places in the universe where the architecture is pushed beyond its limits, where the curvature becomes so steep and the gravity so intense that the very laws of physics as we know them begin to unravel. These are the black holes, the ultimate knots in the tapestry of existence. At their edge lies the most mysterious boundary in all of science, the event horizon. This is the 7th chapter of our exploration, a descent into the threshold of the unknown, where the cosmic speed limit creates a one-way door, and where the concept of now and forever loses all meaning. To understand the event horizon, we must return to the concept of escape velocity. On Earth, if you throw a ball upward, it eventually falls back down because of the planet's gravity. To leave Earth entirely and travel into space, you must launch an object at a speed of about 11 kilometers per second. If you were on a more massive and denser planet, the escape velocity would be higher. A black hole is essentially an object so dense that its escape velocity exceeds the speed of light. Since we know from our earlier chapters that nothing in the universe can travel faster than light, it follows that nothing, not even light itself, can escape from a black hole once it crosses a certain threshold. This threshold is the event horizon. It is not a physical surface like the crust of a planet. It is a mathematical boundary in the geometry of space-time. Once you pass it, the path to the outside world simply ceases to exist. This boundary is often called the point of no return, but its implications for the fabric of space-time are much deeper than just a trap for light. In general relativity, the event horizon represents a place where the directions of space and time effectively swap roles. In our normal lives, we have freedom of movement in space. We can go left or right, forward or backward, but we have no freedom in time. We are always forced to move from the past toward the future. Inside the event horizon, the gravitational curvature is so extreme that all possible paths in space lead toward the center of the black hole. Because the center is in your inevitable future, moving outward becomes as impossible as moving backward in time. The geometry of the universe has twisted in such a way that the center of the black hole is no longer a place you go to, but a time you arrive at. This distortion creates a terrifying reality for an observer watching someone fall into a black hole. Because of the gravitational time dilation we explored in Part 5, gravity slows down the passage of time. As an object approaches the event horizon, the gravity becomes so strong that its clock appears to tick slower and slower from the perspective of an outside observer. If you were watching a friend fall into a black hole, you would see them move in slow motion. As they reach the edge, they would appear to freeze, their image reddening and fading as the light they emit is stretched to infinite wavelengths by the intense gravity. To you, they would never actually cross the horizon. They would simply linger there like a ghost at the edge of time, eventually disappearing as the light becomes too faint to detect. However, the experience for the person falling in is completely different. From their perspective, their own clock ticks normally. They would fall through the event horizon without feeling a sudden bump or seeing a physical line in space. But they would witness something extraordinary as they looked back at the universe they were leaving behind. Because their time is slowed relative to the outside world, they would see the entire future history of the universe play out in a frantic, accelerated blur. They would see stars live and die, galaxies collide, and the very cosmos evolve in the moments before they cross the threshold. Once inside, they are severed from the rest of reality. No signal they send can ever reach the outside, and no force in the universe can stop their descent toward the center. As the falling observer moves deeper into the black hole, they encounter the phenomenon of spaghettification. Because gravity follows the inverse square law, it is much stronger at their feet than at their head. In the extreme environment of a black hole, this difference, known as a tidal force, becomes so powerful that it literally stretches the person's body into a thin, long strand of atoms. The fabric of space-time itself is being pulled apart so violently that even the fundamental forces holding matter together cannot compete. This is the physical manifestation of the geometry's collapse. The straight paths that matter follows in space-time have become so divergent that nothing can remain whole. The ultimate destination of this journey is the singularity, the point at the very center of the black hole where the mass of a giant star has been crushed into a region of zero volume and infinite density. Here, the curvature of space-time becomes infinite. This is the moment where our understanding of the universe fails. Einstein's equations of general relativity, which have been our guide throughout this series, return answers that make no sense. They produce infinities. At the singularity, the fabric of space-time is not just curved, it is torn. Space and time as we define them cease to exist. This is the great breakdown of modern physics, the place where the world of the very large, governed by gravity, meets the world of the very small, governed by quantum mechanics, and the two theories refuse to speak the same language. The event horizon also presents us with a profound mystery known as the information paradox. In our universe, information, the data that describes the state of every particle, is supposed to be preserved. But if an object falls into a black hole and is crushed into a singularity, what happens to that information? Does the universe forget what the object was? If information is lost, it would violate the core principles of quantum mechanics. Some scientists suggest that the information is actually encoded on the surface of the event horizon, like a two-dimensional hologram of a three-dimensional object. This led to the radical holographic principle, the idea that our entire three-dimensional universe might actually be a projection of information stored on a distant two-dimensional boundary. The event horizon, therefore, is not just a graveyard for matter, but perhaps a library of everything that has ever been lost to the void. As we stand at this boundary, we realize that black holes are more than just cosmic vacuum cleaners. They are the ultimate test subjects for the architecture of reality. They show us that space-time has a breaking point, and they challenge us to find a deeper theory that can explain what happens when the fabric of existence is destroyed. They are the places where the invisible architecture reveals its most hidden secrets, forcing us to reconsider the nature of information, entropy, and the very origin of the cosmos. But if space-time can be torn and twisted into such extreme shapes, we must ask if it can be manipulated in other ways. If we can have a hole in the fabric that leads to nowhere, could we have a tunnel that leads to somewhere else? In our next chapter, we will move from the one-way door of the event horizon to the theoretical shortcuts of the universe. We will explore the concept of cosmic shortcuts, wormholes, and ask whether the geometry of space-time allows for bridges between distant stars, or even between different times. we will see if the elasticity of the fabric that we have studied can be harnessed to bypass the cosmic speed limit and turn the vast distances of the universe into a manageable neighborhood. The vastness of the universe is perhaps the most humbling realization of the modern age. As we have seen in our previous chapters, even at the maximum speed allowed by the laws of physics, the cosmos is a place of profound isolation. To reach our nearest neighbor star, Proxima Centauri, would take more than 4 years at the speed of light, and tens of thousands of years with our current propulsion technology. The edge of our own galaxy is tens of thousands of light years away, and the nearest major galaxy, Andromeda, is millions of light years distant. Under the strict rules of the cosmic speed limit, the human dream of interstellar travel seems destined to remain a fantasy confined by the sheer scale of the space-time fabric. However, the very equations that gave us the speed limit and the curvature of gravity also hint at a radical loophole. If space-time is an elastic, flexible medium, then perhaps we do not need to travel across it at all. Perhaps we can simply fold it. This is the 8th chapter of our investigation into the invisible architecture of reality, an exploration of cosmic shortcuts, the theoretical bridges through the fabric of existence known as wormholes. The concept of a wormhole, or more formally an Einstein-Rosen bridge, was born from the same mathematics that predicted black holes. In 1935, Albert Einstein and his colleague Nathan Rosen realized that the geometry of a black hole could, in theory, be connected to another point in spacetime. Imagine the space-time fabric as a flat sheet of paper. To get from one side to the other, you must travel across the entire surface. But if you were to fold that paper so that the two distant points touched, you could poke a hole through both layers, creating a shortcut that bypasses the distance entirely. In the four-dimensional reality of our universe, this would appear as a spherical entrance, a mouth that leads through a throat and exits at another spherical mouth somewhere else in space, or even somewhere else in time. This is not a journey through the void of space, but a journey through the bulk, a higher dimensional shortcut that defies our three-dimensional intuition. To understand how such a structure could exist, we must look at the Schwarzschild solution, the first mathematical description of a black hole. When Karl Schwarzschild solved Einstein's equations, he found a geometry that described a point of infinite curvature. Einstein and Rosen realized that if you followed the mathematics to its logical conclusion, the singularity of a black hole could act as a bridge to a mirror universe or a distant part of our own. In this model, a black hole on one side would be connected to what is called a white hole. On the other, an object that behaves exactly like a black hole in reverse, constantly spewing matter and light out rather than sucking it in. While white holes have never been observed and are considered highly speculative, the mathematical possibility of this bridge remains one of the most tantalizing prospects in all of theoretical physics. However, the universe does not give up its secrets easily, and the laws of physics seem to have built-in defenses against these shortcuts. The first and most significant problem is stability. According to general relativity, a natural wormhole formed by the collapse of a star would be incredibly unstable. The moment any matter, or even a single photon of light, attempted to enter the throat, the gravitational forces would cause the wormhole to pinch shut and collapse into a singularity faster than the light could pass through. To an observer, the wormhole would look like a black hole that forms and disappears instantly. To make a wormhole traversable, meaning a human being could actually fly a ship through it and come out the other side, we would need a way to prop the throat open against the crushing force of gravity. This brings us to the most exotic requirement in physics: exotic matter. To keep a wormhole from collapsing, we would need to line the throat with a substance that possesses negative energy density or negative mass. In our everyday world, all matter has positive mass and exerts an attractive gravitational pull. Negative mass, however, would exert a repulsive gravitational force. It would literally push space-time outward. This anti-gravity effect would counteract the inward pull of the wormhole's gravity, holding the bridge open for travel. While this sounds like the stuff of pure science fiction, the existence of negative energy is actually supported by quantum field theory. The Casimir effect, for example, demonstrates that between two very close metal plates in a vacuum, a region of negative energy density can be created. The challenge is that we would need a titanic amount of this exotic energy equivalent to the mass of a planet to keep even a tiny wormhole open. The implications of a stable wormhole extend far beyond mere travel. Because space and time are fundamentally linked, a shortcut through space is also, inevitably, a shortcut through time. If you were to create a wormhole and move one of the mouths at relativistic speeds while keeping the other stationary, the time dilation we studied in Part 3 would cause the two ends of the bridge to exist at different times. You could step into the moving mouth in the year 2300 and exit the stationary mouth in the year 2025. This would create what physicists call a closed time-like curve, a path through space-time that allows you to return to your own past. This realization forced scientists to confront the terrifying paradoxes of time travel, such as the grandfather paradox. What happens if you go back in time and prevent your own birth? Because of these paradoxes, some physicists, including the late Stephen Hawking, proposed the chronology protection conjecture. This hypothesis suggests that the laws of physics will always find a way to prevent time travel from happening, perhaps by causing the wormhole to explode the moment it is created due to a buildup of vacuum fluctuations. Nature, it seems, may have a built-in reset button that preserves the sequence of cause and effect. Yet, the debate remains open. We do not yet have a complete theory of quantum gravity, a theory of everything, to tell us for certain whether wormholes can exist or if they are simply a mathematical mirage. Despite these hurdles, the study of wormholes is not just a pursuit for science fiction writers. It is a vital part of our attempt to understand the deepest structure of the universe. In recent years, a radical new idea has emerged in theoretical physics called ER equals EPR. This hypothesis suggests that the spooky action at a distance observed in quantum entanglement, EPR, is actually caused by microscopic wormholes, connecting particles across the universe. If this is true, it would mean that the space-time fabric is not just a smooth sheet, but a complex web of billions of tiny quantum bridges. It would suggest that entanglement is not just a strange quirk of particles, but the very glue that holds the fabric of space-time together. As we stand on the edge of this realization, we find ourselves moving from the grand, sweeping curves of the cosmos to the smallest possible scales. If the universe is built of these connections, then the smooth fabric we have been discussing might be an illusion. Just as a piece of silk looks smooth from a distance but is revealed to be a weave of individual threads when viewed under a microscope, space-time itself might have a granular, pixelated structure. To truly understand the architecture of reality, we must look past the stars and the black holes and dive into the subatomic realm, where the geometry of gravity meets the chaos of the quantum. In our next chapter, we will explore the quantum pixel and ask whether space-time is actually made of something deeper, something that isn't space or time at all. Throughout our investigation, we have treated the space-time fabric as a smooth, continuous, and elegantly curved surface, a cosmic canvas that bends under the weight of stars and stretches with the movement of galaxies. This is the majestic view provided by Albert Einstein's general relativity, a theory that has stood unchallenged for over a century in its ability to describe the macro world of the very large. However, as we descend from the scale of galaxies and black holes down into the subatomic realm, we encounter a profound and unsettling crisis in the heart of physics. Our universe is not just governed by the vast, smooth geometry of gravity. It is also ruled by the chaotic, jittery, and probabilistic world of quantum mechanics. When we try to merge these two great pillars of science, the mathematics doesn't just struggle, it collapses into nonsense. We discover that the smooth fabric we have been discussing may be a grand illusion of scale. Much like the smooth, vibrant images on a high-definition screen are actually composed of millions of individual, discrete pixels. In this 9th chapter, we dive into the mystery of the quantum pixel to ask, is space-time actually made of something? Does the architecture of reality have a bottom scale, a fundamental graininess beyond which space and time as we know them simply cease to exist? The conflict at the center of modern physics is the clash between the continuous and the discrete. In Einstein's world, space is a continuum. You can take a meter of space and divide it into a billion parts, and then take one of those parts and divide it into a billion more, and you can repeat this process forever. In this view, there is no smallest unit of distance. The fabric is infinitely smooth. But quantum mechanics tells us a very different story about everything else in the universe. We know that matter is not a continuous slurry, but is made of discrete atoms, which are in turn made of quarks and electrons. We know that light is not a continuous wave, but is composed of individual packets of energy called photons. Everything we can touch, see, or measure seems to come in chunks or quanta. It seems profoundly unlikely that the stage itself, the very fabric of space-time, would be the only thing in the universe that is infinitely divisible. If the universe is built of discrete building blocks, then logic dictates that space and time must also be quantized. There must be a fundamental unit of space, a quantum pixel, that represents the smallest possible distance allowed by the laws of nature. This fundamental scale is known as the Planck length, named after Max Planck, the father of quantum theory. The Planck length is approximately 10 to the power of -35 meters. To visualize how incredibly tiny this is, we must use a scale of magnification that defies human intuition. If you were to take a single atom of hydrogen and magnify it until it was the size of the entire observable universe, the Planck length would still only be about the height of a human being. It is at this unimaginably small scale that the smooth, predictable geometry of Einstein finally shatters. When we attempt to apply the rules of gravity to distances this small, the energy fluctuations required by quantum uncertainty become so violent that they warp space-time into a turbulent, foaming mess. This is the realm of quantum foam, a term coined by the physicist John Wheeler. At the Planck scale, the very concepts of before and after, or left and right, may fluctuate or lose their meaning entirely. Space-time here is not a stable fabric, but a boiling, chaotic sea where microscopic black holes and wormholes might blink in and out of existence in the smallest fraction of a second. One of the leading attempts to describe this pixelated reality is a theory known as loop quantum gravity. This theory suggests that space is not a void that objects sit in, but is instead a physical entity made of discrete loops of gravitational field lines woven together. These loops form a complex, three-dimensional web called a spin network. In this view, space is very much like a piece of chainmail armor. From a distance, the chainmail looks like a single, flexible, and continuous sheet of metal. But as you zoom in, you see that it is actually composed of individual, interlocking rings. There is no such thing as the space between the rings, because the rings themselves are the space. According to loop quantum gravity, there is a smallest possible volume of space, roughly a Planck length cubed, and a smallest possible tick of time. When you move through the room, you are not sliding smoothly through a void. You are jumping from one node of the spin network to the next, like a character moving across the pixels of a video game map. Another powerful perspective comes from string theory, which proposes that the fundamental building blocks of the universe are not point-like particles or loops of space, but tiny, vibrating strings of energy. These strings are so small that they appear as particles to our crude instruments, but their different vibrations create the various particles and forces we observe, including gravity itself. String theory suggests that space-time is a background that these strings inhabit, but it also hints that there are many more dimensions than the four we can perceive dimensions that are curled up at the Planck scale. In this model, the pixels of our reality might be the specific ways these extra dimensions are folded. The geometry of the invisible architecture is far more complex than we ever imagined, involving a hidden landscape of 6 or 7 additional dimensions that dictate the laws of physics in our familiar four-dimensional world. But perhaps the most radical and modern idea in this field is that space-time is not made of anything physical at all, but is an emergent property of quantum information and entanglement. This is the concept often summarized as it from qubit. Some of the most brilliant minds in physics today are exploring the possibility that space is not a fundamental part of the universe, but is something that grows out of the quantum connections between bits of information. We know that particles can be entangled, meaning their states are linked regardless of the distance between them. There is an emerging mathematical proof suggesting that the geometry of spacetime is actually a map of these entanglements. Just as the temperature of a gas is not a property of a single molecule but emerges from the collective motion of billions of atoms, the fabric of spacetime may be a macro-scale phenomenon created by the collective entanglement of quantum states. If you were to somehow break all the entanglements in a region of the universe, the space in that region would literally cease to exist. Objects would no longer have a distance between them because the glue of space would be gone. This suggests that the invisible architecture we have been investigating throughout this series is actually a holographic projection of quantum data. The 3 dimensions of space we see around us might be a lower dimensional set of information projected into a higher dimensional volume, much like the 2-dimensional surface of a credit card hologram creates the illusion of a 3-dimensional image. If this is true, then the quantum pixel is not a little chunk of matter, but a bit of information. The universe is not a collection of things moving through space. It is a processing of data that creates the illusion of space. This realization brings us to the ultimate boundary of science, where physics meets philosophy, and where the study of gravity becomes the study of information itself. If space-time is indeed pixelated, emergent, or holographic, It changes everything we know about the history of the cosmos. It suggests that the Big Bang was not just an explosion of matter into a pre-existing void, but the moment when the pixels of our reality first began to assemble, the moment when information first began to organize into the geometry of space and the flow of time. It means that the beginning of the universe was the birth of the architecture itself. As we move into our final chapter, we must take all these mind-bending concepts, the bending of the fabric, the theft of time, the ripples of waves, the traps of black holes, the shortcuts of wormholes, and the graininess of the quantum scale, and apply them to the grandest story ever told. We will look at how this four-dimensional block of space-time began, how it is currently being pushed apart by the mysterious force of dark energy, and what the ultimate fate of the invisible architecture will be. Is our space-time fabric eternal, or is it destined to be torn apart in a final big rip, or perhaps to dissolve back into the quantum chaos from which it emerged? We have traveled through the most profound mysteries of the cosmos, from the realization that space and time are a single, elastic fabric, to the discovery that this fabric can be stretched, warped, and even torn. We have seen how gravity is the shape of this architecture and how time is a variable determined by motion and mass. We have explored the ripples of gravitational waves and the terrifying boundaries of black holes. Now, we arrive at the final chapter of our journey, the story of the space-time fabric itself, where it came from, how it is evolving, and how it will eventually end. If the universe is a four-dimensional block, then we must look at the edges of that block to understand the ultimate fate of reality. This is the story of the beginning and the end, a narrative that spans nearly 14 billion years of history and looks forward to a future so vast it humbles even the stars. The story begins at a point of infinite density and temperature known as the singularity. According to the Big Bang theory, the universe did not explode into an empty void. Rather, the space-time fabric itself was born and began to expand. In the first trillionth of a second, the universe underwent a period of inflation, where the fabric stretched at a rate much faster than the speed of light. This was not a violation of the cosmic speed limit, because it was space itself that was expanding, not objects moving through it. This initial burst of growth smoothed out the fabric, creating the vast, flat geometry we observe today. In those first moments, the architecture was a hot, dense soup of energy, and as the fabric stretched, it cooled, allowing matter to condense, stars to ignite, and galaxies to form. The history of the universe is, in essence, the history of the space-time fabric growing and carrying matter along with it. For many years, astronomers wondered whether this expansion would eventually slow down. Logic suggested that the collective gravity of all the stars and galaxies should act like a cosmic brake, pulling the fabric back together. There were three main theories for the fate of the architecture. The first was the Big Crunch, where gravity eventually wins, the expansion stops, and the fabric collapses back into a singularity, perhaps to trigger another Big Bang in a cycle called the Big Bounce. The second was a Goldilocks scenario, where the expansion slows down but never quite stops, reaching a perfect balance. The third was the Big Freeze, where the expansion continues forever and the universe becomes cold, dark, and empty. To find the answer, scientists in the late 90s looked at distant exploding stars to measure how fast the universe was expanding in the past compared to now. The result was one of the greatest shocks in the history of science. The expansion of the universe is not slowing down, it is accelerating. Some mysterious force is pushing the space-time fabric apart. acting as a kind of anti-gravity. Scientists call this dark energy. It appears to be an intrinsic energy of space itself. The more the fabric stretches, the more space there is, and therefore the more dark energy there is to push it further. This discovery changed our understanding of the end of the story. If dark energy continues to dominate, the future of the space-time fabric is one of ultimate isolation. In about 100 billion years, the expansion will have pushed all other galaxies so far away that their light will no longer be able to reach us. The Milky Way will become a lonely island in an infinite dark void, and the past light cone we discussed in earlier chapters will shrink until the visible universe is empty. But the fate of the fabric depends on the nature of dark energy itself. If dark energy remains constant, we face the Big Freeze, also known as heat death. In this scenario, stars will eventually run out of fuel and go dark. Black holes will slowly evaporate over trillions of years through a process called Hawking radiation. Eventually, the universe will reach a state of maximum entropy, where no more energy can be used to perform work. The space-time fabric will continue to exist, but it will be a cold, static, and lifeless void where nothing ever happens again. Time will still exist as a dimension, but without change, the very concept of the flow of time will lose all physical meaning. The universe will be a vast, frozen museum of a history that no one is left to remember. However, if dark energy becomes stronger over time, a theory known as phantom dark energy, we face a much more violent end, the Big Rip. In this scenario, the acceleration of the expansion becomes so extreme that even gravity can no longer hold galaxies together. The fabric stretches so violently that galaxies are torn apart, followed by stars, then planets, and eventually atoms themselves. In the final fraction of a second, the very fabric of space-time is shredded, and the architecture of reality is destroyed. The invisible architecture that has held the universe together for billions of years simply ceases to exist, leaving behind a nothingness that cannot even be described as space or time. This is the ultimate breakdown of the geometry we have studied. A third, more hopeful possibility is the Big Bounce. Some theories of quantum gravity suggest that space-time has a minimum size and cannot be crushed into a true singularity. If this is true, then a big crunch would not be the end, but a transition. The fabric would collapse until it reached the quantum scale, at which point the repulsive forces of quantum mechanics would cause it to rebound in a new Big Bang. This suggests that our universe might be just one in an infinite chain of universes, a cosmic heartbeat of expansion and contraction that has no beginning and no end. In this view, the space-time fabric is eternal, constantly recycling itself into new forms, new stars, and perhaps new civilizations. Regardless of which ending is true, the study of the space-time fabric has transformed our place in the cosmos. We have learned that we are not separate from the universe, looking at it from the outside. We are woven into its very structure. Every atom in your body, every thought in your mind, and every moment of your life is a coordinate in a four-dimensional masterpiece. The invisible architecture is the most fundamental thing we can know, a structure that is both the stage and the actors, the clock and the time, the void and the matter. Understanding it is the ultimate achievement of the human intellect, allowing a biological creature on a small, blue planet to grasp the laws that govern the entire expanse of existence. As we conclude this journey, we find ourselves back where we started, looking up at the night sky, but now we see it with new eyes. We no longer see a static void of stars. We see a dynamic, vibrating, and curved fabric. We feel the theft of time as we stand on the ground. We sense the ripples of distant collisions in our very atoms, and we recognize that the present moment is a beautiful, personal illusion. The space-time fabric is the greatest story ever told, a narrative written in the language of geometry and energy, and we are the witnesses who have learned to read its pages. We are the universe observing itself, and in that realization, we find our true home. Good night, and see you in the next video.